All right. Our next speaker's name is Suela Isaj, and she is representing Denmark. She is a data and machine learning engineer at Churney, a company in Copenhagen. And she also has a PhD in computer science, focusing on entity extraction and resolution. So I would say that makes her quite an expert in the field. And she is now going to talk to us about data warehouse ingestors. And we said that's a very natural step after the instrumentation. So Suela, go ahead.
Yeah, I'm so happy actually to be here. Thank you so much for such a sweet introduction. And for people who are in Copenhagen, I hope you're seeing the first snow of the season. It's so pretty. And couldn't be like a best place to actually be presenting this topic. I would now just go share my screen and let me go for it. Yeah. So, I am Suela, and I will be presenting today across data warehouse ingestors, specifically focusing on importing data on BigQuery. Some few words about me. I work as data ML engineer at Churney, and I have a background in computer science and data. I hold a joint PhD in data extraction and integration between Aalborg University and Université Libre de Bruxelles, and I have over 5 years of experience in data engineering. So I work at Churney. Churney is a startup that offers causal ML solutions. We actually try to optimize the company's acquisition campaigns by sending a signal to Meta and Google to be able to target users with a high lifetime value. In such a way, the algorithms in Meta and Google can actually optimize to bid on these customers, to bid on these users for the company. While we do that, it actually becomes also easy for the company to optimize the ad spend of the campaigns, such as focusing on the best performing ones. Apart from the acquisition efforts, we also offer solutions on retention as well. We have solutions to be able to retain high lifetime value customers and also offer the correct treatment for each customer, such as trying to increase their lifetime value and also try to prevent churn. We have also a website, and there is different use cases there about Churney and the different products that we offer in ML. Okay, so about this topic and what is the use case, why I'm bringing this topic here. As I said, we need these ML models that use data from our client data warehouses. And our clients is not guaranteed that they will be on GCP like we are at Churney. Our data stack is on GCP. So it means that we might have to load data from completely different data warehouses and different providers. So we need to have support for different data warehouses, first of all, having these integrations. Then we have to do some work on finding the correct permissions to have minimal access on their end. So we actually are able only to access what's allowed for us. We have to have cost considerations because we could be moving tons of data and that could end up being actually expensive for the client and also for us. And when the data arrives on the destination, which is in our BigQuery, we have to make some modeling trade-offs. And I'll go a bit over the process here. So about the data warehouse unload process, the process starts with unloading the data onto a bucket on the client platform. This means that if the client is on Athena or on Redshift, that would be S3. Then from the data from the platform specific bucket, moving it to Google Storage, which would be on our end. And finally, loading data from Google Storage to BigQuery. This is basically the main steps of the process if I were to simplify it. While we do all of this, we have, of course, to deal with permissions. The first one, we need access on the data set and on the table that the client has prepared for us, and just on that. We also need access to the metadata, and we use this to optimize our extraction. And finally, we need to unload data on a bucket. So, of course, we need those permissions in place so we are able to unload from their tables to their bucket. The rest of the permissions, then, they are on our end. But this is what we have to take care from the client side. So if I were to put the process in one diagram, all of it, this is how it would look. On the left side, we have the data warehouses that we support now. We're thinking to add more integrations in the future. If the client is on Athena, on Redshift, or Databricks on AWS, then the data will be unloaded into an S3 bucket. If the client is on Max Compute, this is on Alibaba Cloud, then it will be an OSS bucket. If the client is on Databricks on GCP or on Snowflake, we actually have a way to build a direct integration from those to our Google storage. If the client was on the other data warehouses, then we would have to have a step that moves the data from S3 or OSS into Google storage. Once the data is in Google storage, it means it's on our platform. And then we ingest that in a temporary data set, the way it is. And from that, we merge it to the final data set. If the client is on BigQuery, the process becomes way simpler. Actually, GCP doesn't care much which is the organization. It's considered like running data between two different projects. As long as you have the permissions, the correct permissions in place, then you can run a merge, selecting data from the client and putting it on your project. So the process, as you can see, it's way simplified. So as I have put here, like the keyword reusability, it's completely different ingestors that we try to bring on BigQuery. So we are trying to reuse some code and have some similar patterns. For that, we decided to go for SQL Alchemy, which is a Python library to deal with the different data warehouses. It has advantages, and the advantages that we have seen is that it has a cross-platform compatibility and handles the different SQL dialects. This means that I don't have to worry much about which data warehouse I'm talking to. SQL Alchemy will take care about this. And also the interesting part is like for each of these different platforms, I need to create, let's say, an SQL Alchemy engine. The parameters will change depending on which data warehouse I would like to connect. But once I have the engine, then I can create sessions, I can submit my queries, and that will be similar across the different data warehouses. So it makes very easy for us to use it across the different ones. It reads metadata efficiently, which means I can create, let's say, a SQL Alchemy table, and I have access to the columns, to the data types, and all this information about the table without me having to do specific queries and try to have like specific interactions with different data warehouse to read this information. And of course, it's uniform across the different clients, so the different integrations, so we can reuse code. And this makes it pretty nice. However, we have seen some disadvantages, and one of them that it's actually not so nice to be lacking features. Sometimes we look at the native library for that data warehouse and we see that some feature exists. When we check on SQL Alchemy, the support isn't there. It's not always common, but when it's there, we have to find a way around. Or it could be actually the case that it is even supported, but it's lacking in the documentation. So you have to go to the source code and try a bit more, trying to actually be able to use the feature you think it's needed for the integration. As I said, it's pros and cons. Up to now, it has been more advantages for us, so we have been very happy having this unified way to talk to the different data warehouses with SQL Alchemy. However, code reusability doesn't mean only which libraries you use. It also has to do about the coding patterns. We have decided to go for an ingester class, from which the different ingestors will inherit from, because the ingester class kind of wraps the process pretty nicely together, and then it has the methods that we need to implement for the different specific ingestors. We have these two main methods, prepare and ingest. Prepare will log the available tables, prepare the metadata for these tables, and try to optimize the ingestion strategy. While the ingest method is kind of like a continuous process between the steps. It just makes sure that we keep going through the states. It's basically saying while there is still a state, continue ingesting. So it wraps the process together, let's say. And the states is what we actually saw in the diagram. It's a bucket unload to the client side. It is the Google Storage bucket transfer, ingesting data to the temporary data set, to the final data set, and we log some details in a state table so we know how long the ingester lasted, how many rows it ingested, and so on. So that's why this arrow here, because while there are steps, it will continue ingesting. The ingester class turned out to be we were quite happy with going with this coding pattern because we have a consistent interface between the different ingesters. We know what to expect. We know which methods we need to implement and how the process should go. They share functionality. As you noticed from the diagram, when we move the data up to the Google Storage bucket, then the process is the same. So we could be using the functions the same across the different ingestors, and that makes it pretty easy. We can add new platforms without being a pain. We have brought new ingestors quite with an ease because we know exactly which steps to implement. We already have, let's say, the skeleton of what we need to do. And then up to, as I said, we bring the data to the Google Storage, then the process continues on its own between the steps. We can plug new states at any point, and this process allows us to do that because you can just put a step in the middle, making sure that the previous state will return it and the next one will read from it, and then the process, it's all together wrapped up. We did that when we were unloading data on our Google Storage, and we wanted to add some logging to see how many megabytes we are loading in each sync for each table, just to add some observability about the amount of data we're unloading. And the process was actually, it took maybe 2 hours to add this state in place. This is my favorite one, independent integration tests. If you want to have integration tests for your ingestors, and if you want like a full one from beginning to end, that's kind of a bit of a pain. But with the different states and the way we have split the code, it's pretty nice to be able to test the state fully from beginning to end, putting, let's say, some data on S3, and then making sure that it's the same data going to Google Storage in the end, and the process behaves as it should be. So we have these tests also in CI/CD. So if someone is doing some change, then we know how it's affecting our ingestors. Okay, so it's a big diagram and moving data along with this process. What about cost? We could be moving lots of data, terabytes of data up to BigQuery, and that could end up being expensive. The cost is related not only of how much data we're moving, how much we're selecting from the client side, but also how we merge it on our end. I will bring an example here from BigQuery, just to show why an incremental load can be better than a full load sometimes. This is a table that is 83 terabytes. I'm doing a select start from the table, basically scanning all the data. And this is when I put a condition about just selecting only one partition, only one day of the data, and it's 28 gigabytes. So it's 3,400 times larger to do a full select on the table. And if we were to actually, in each of the syncs, select the table and replace it on the destination, then we would end up paying, it's $5 per terabyte. It is $415 per sync for the first case. And I'm sure this is not a big amount of money for a company in the beginning, but once you have to schedule this, and our syncs run every 4 hours for a month, this will end up being $74,700, while the incremental load, just selecting this data, is just $25. And believe me, I ran the numbers a lot of times, and it actually ends up having this big margin in the cost. So if you are in this case, you might have to think of doing incremental loads. When to use incremental loads? Well, when you have big data. If you don't have big data, there is really over-engineering, trying to just select a part of the data and then worrying how you're going to merge this in the destination. You might even ending up by the joins and everything, actually scanning more data. So if it's not big data, don't bother. If the data is updating frequently, but only on a subset of data, what I mean with this is, let's say we have event data, and this event data, the events of the previous month, there's nothing to look in those. They are well defined. The properties are all there. All events are backfilled. All is good. But the events of the last, let's say, 3 days that keep updating, the properties get more accurate. So you might need to sync those again more frequently. That's a perfect case for incremental load. So you can actually focus only on the events that keep updating without touching the rest of the partitions. If the data is immutable, it's perfect. Then it means an event, once it happens, it's well defined, no one is mutating the record anymore. It's a perfect case for an incremental load. Then select the data from the source, put it on the destination, and design your incremental loads. So the strategy should be to generally reduce the amount of data to unload on the source data warehouse. So try to pick as small amount of data from the source, preferably using time-related conditions, using where conditions, and make sure you're hitting the partitions on the client data warehouse. If it's BigQuery, it should be the partition column. If it's Athena, they usually split by year, month, day. So go in the correct path to pick the data and don't scan the whole thing. So then it becomes quite cheaper on their end. There is also another thing, have a good merge strategy on the destination. So what's an efficient merge? Okay, this is how a merge would look like, a typical merge joining on the key of the tables. And try to imagine we don't have the blue lines for now. So we are merging data from the source to the destination. If they join, if you find it in the source and the destination, we updating it. If we find it on the source but not on the destination, then we need to insert it. And if it's not in the source anymore, most probably it was some error, then delete it. If we are not filtering on the partition, then we'd be actually joining the whole destination table with, let's say, this small amount of data we got from the source on the key to update the data. We end up anyway scanning the data. You could put actually a clustering on the key, and then that becomes way more performant. However, if you have a case of data that is immutable or data that is updating only on some partitions, then you can add the blue lines here, and then you only operating on one partition. This means that from terabytes of data, you end up scanning only gigabytes, and that becomes quite cost effective. You can even go further by doing the merge procedure on the right. When you say, I want to merge on false, which means I don't want to even join these two sets. I just want to drop the last partition and put it from the source. And this is when you're actually trying to be really cost effective and trying to just scan the data almost linearly. There are benchmarking strategies out there, and this is a nice article from DBT where you can see how they scale, how it scales when you have a full refresh, when you actually pull data from the source and just drop it on the destination, and how it scales when you have the merge here on the right. It's the orange line. It's not a lot of data in this example. It goes up to 200 gigabytes. So let's say that it's not shocking you, the graph, but these numbers can really escalate very fast when you have a lot of data. And I'll say just a few words about the modeling the data on the destination now. We brought the data on the final place on BigQuery. What do we do? At Churney, we have decided to take some decisions regarding modeling and storing data on the destination that are driven by cost or by the complexity. We do minimal changes, though. We generally go for an ELT procedure, just taking the data from the source and dropping it on the destination. We do minimal changes as if there is a date time or Unix time that we need to make it as timestamp because we want to have partitions and clusterings on our end. Then we will do this casting on the data. However, the rest of the data will be moved the way it is. We do full loads on relatively small tables because, as we said, it's not worth dealing with an incremental load, but also means that we are not ensuring that the schema is the same, so it could be changing. This means also that not just the schema, but the records could be changing on these tables, and we have to deal with that issue. If these are events, the way we deal with it is mostly we have like a bigger load windows saying that the events can continue changing for a week, unfortunately. So we will try to override them from the source each and every time, and that becomes a bit better. If we have records that they can actually mutate in place, like customer data, for example, initially we go with this functionality that is called time travel in BigQuery, where you can see how your table looked up a week ago, some days ago. You can decide how much back you want in time, and then you can see that if by joining this snapshot of data with your data, you can see if data is mutating in a wild way or in a way that is affecting your ML models. And if the features that are changing are important to you, then you might have to go for a slowly changing dimension. I put type 2, that is the most common one, but any type would maybe work in this case. In that case, you would have to keep versions of your entities and how they are mutating over the history. This modeling decision, of course, it's a bit more expensive because then you have to do merge a lot of times on the data, the new snapshot, and what you have on the destination, and trying to maintain the versions. But if this brings value to your ML model, then I guess that's the way forward. Okay, so in summary, I would say that having different ingestors from different data warehouses might look scary, but trying to establish a unified approach to handle the data ingestion will pay off. It will simplify the integration and it streamlines the operations. Cost can become a driver for your pipeline decisions. In the beginning, it might be like this small thing, this addition that you are looking in your data. Okay, it's costing a bit more, but then you have to think how this will scale, how this will scale when I increase the frequency of my syncs, how this will scale when I'm dealing with large amounts of data, because the tables, they only grow, they never get smaller. We add history, and you have to think of that when you are designing your pipelines. Incremental loads are a natural solution for immutable events. Don't be scared of them. They used to exist in data engineering back in the days. The old DB admins, they did incremental loads and they dealt with versions of the different entities. So think about that and how that can make it cost effective, how that can make it faster for your syncs, and how it makes sense for you to implement incremental loads rather than just dropping the data on the destination and moving them from the source. Try to do minimal modeling at the initial layer of the data warehouse. It actually helps you maintain the flexibility. Every time you need to sync data, if you have put these complex transformations on the go and something goes wrong, then you have to go back every time, try to fix your sync while the data is not fresh anymore and everyone is complaining. So try to allow yourself this flexibility when you're loading the data, and then try to have more checks once the data is landing on your data lake or initial layer of the data warehouse. So then you have the control over how would you like to transform the data and how you would like to model this forward. Okay, thank you.
Hello, thank you so much. Well,
I try to rush a bit so I have time.
yes. I loved your hot take that you should not fear the incremental loads.
No, not at all.
They became uncool, but let's make them cool again.
Yeah.
All right, so let's do some questions. We have a question from Charlotte. What are your considerations when using open source like SQL Alchemy in this type of product? What do the clients say?
We are actually a big fan of open source because the code is open, which makes us look at every functionality, how is implemented, if we like it, if we don't like it, and if we want to actually just have a change in it, then you can do a pull request and you contribute in those. So we are actually a big fan of open source, and I would say like SQL Alchemy is a Python library overall. It's not even a framework you have to tie yourself into. It's like using, I don't know, pandas or everything we use in Python. So we're a big fan of open source at Churney.
But so there's no issue for on your client's end. They don't have a problem with that.
If we weren't using SQL Alchemy, then we would be using Boto3. So it's kind of the same. If we need to get access to the data in AWS, that's the library you use. And SQL Alchemy is basically just a layer on top of it, trying to implement the different features and trying to access the data. We have to do it with some library in the end. So this would be one of the solutions.
All right. We have another question from Jayant. What about data such as semi or unstructured data and vector embeddings? Do these kind of data also sync well with SQLA?
We actually don't have this use case, so I don't know how that will actually scale. We mostly have text data, we have JSON data. There is JSON data in columns, so the data is, in the end of the day, again tabular, which makes it pretty simple for SQL Alchemy to read the table and move it forward. We're not moving files, we're not moving any unstructured data, so SQL Alchemy is kind of pretty easy for this use case.
All right. We have another question. What is your rule of thumb to define what small means for a table?
That's a very good one. That's a very good one. And I hope I had a definite answer to this. So if it's, I would say, like if it's some hundreds of gigabytes, up to 100, 200, maybe it's not worth the effort, I would say. But if it gets to like 500 of gigabytes, we're talking terabytes, then you really have to think of the way how you're going to deal with incremental loads. You always know you're losing something with incremental loads. You're not syncing everything from the source. So you're losing this. And if you're not sure if your records are not mutating, so if you don't know if there is backfilling back in the previous partitions, you could go saying, okay, I will do incremental loads. And then the client on their end is saying, well, I see something else on my end. And then you have to explain why you went for, let's say, a cheaper solution and not syncing everything all the time. So I think that if the data is up to a couple of hundreds of gigabytes and you're not syncing it that frequently, that's fine to go for a full load. Also depends how the data is behaving. As I mentioned, if it's updating all over the partitions, you cannot control that. Then you can do incremental loads, let's say during 3 of the things, and in the end of the day you do the full one, trying to have some trade-offs like that. But in the end, it means that the data actually is not really applicable for incremental loads, and you're just trying to save some money by trying to do an incremental load. So I think mostly the use case of the data, like how the records are and how the data is behaving, is a better driver of this decision rather than just looking at the gigabytes or well, if it's terabytes, and then you have to think something.
Interesting. Yeah.
I was going to add also something that we actually copy data on the ROAS form from the client side, which most of the time is also immutable data. If it's events, for example, that come directly from Amplitude, let's say, then it's less likely to be mutating. Usually, records are mutating a lot when they are on the deeper layers of the data warehouse, that there are several queries and someone needs, let's say, the last activity on the user. This is the type of data that we don't prefer, because for the ML models that we run, we need to know exactly at that point in time how the activity and the user looked. And if the records are mutating, then it means we might have information from the future leaking into our training set. And we don't want to do that. We want to have the data as it looked at the time. If some information from the future, such as the customer's last activity, keeps updating, and then we put that in the model, then it means that the moment that we train the model, we have this information from the future and we think we're predicting very well. But then when we put it in production, we might not see that happening. So we're a bit picky with these mutating records. That's why I had that in my slides. We actually keep an eye if something is mutating and we're like, okay, that's not good. Let's not use that feature because it seems like it's mutating.
Yeah, good point. Watch out when stuff is mutating.
It
can go bad.
It's really bad for machine learning models.
Yeah. We need to wrap it up now. And big thank you, Suela. Really interesting. Thank you so much.
Thank you so much for the invite, and such a great community to be in.
Thank you.
Thank